Hello, my name is Irina Voiculescu. I'm from the University of Oxford in the Department of Computer Science. And I'm going to talk about a segmentation algorithm, which, for a change, doesn't rely on any kind of machine learning. So we do very down-to-earth, conventional segmentation. And by segmentation, I mean one of two things. So obviously, our ultimate goal is to segment out features from data, such as a CT or an MRI scan, and you have there parts of our pipeline. So we go from raw data on the left to the 3D model on the right, which we can then measure, 3D print, process in whichever way the clinicians want us to. But in the computer vision community, what is known as image segmentation is the transition from the first image there to the second. So we go from raw data into a collection of regions that somehow belong together. So we partition the image into those regions. And this is where the conventional watershed algorithm comes in. So that's why our paper has watershed in the title. But we have adapted this algorithm in order for it to work with this kind of data. So in particular, unlike the conventional watershed algorithm, where the input was not allowed to contain plateaux, so pixels, areas of pixels of the same grayscale value, we have improved that in order to allow plateaus. And I call them plateaus because there's a metaphor here, and the metaphor comes from the watershed and the whole water idea. So the metaphor is that the grayscale image is regarded as a terrain mapping. So there are the XY coordinates, and then the grayscale is regarded as an altitude. And what the watershed does conventionally is it looks for local minima in that, and then it simulates filling that terrain with water. Obviously, where two catchment areas meet, that's the boundary between the catchment areas, and we then record that as a boundary of one of these regions. I'm going to sweep under the carpet the fact that we actually apply this recursively, and we do some other jiggery-pokery in order to then label the features into the raw data and move on to the 3D model, because that's not the purpose of this paper. So what we do in this paper, like I say, is we deal with those plateaus. And in order to do that, we work not with the raw data, like you see on the left there, but rather we work with the gradient magnitude image. So we look at the steepness in each direction, and we take the magnitude of that vector, and we transform the image into the gradient magnitude, and then apply the modified watershed in that way. So we start from local minima, and we then create paths from each pixel in the image down to those local minima, and create then pointers directly to those catchment basins. And that's where the paths that we build are no longer linear like they were in the conventional watershed, but we convert this to a logarithmic algorithm. And we achieve a significant speed up. So you can see here in the graph below, you can see at the top in blue the algorithm known as the best in the literature. Again, we discuss in the paper why other algorithms have been superseded by that. And we achieve a speed up of about 28% on the Berkeley data set. So we no longer run this on medical data, but rather we took a conventional publicly available data set so as we could make our results reproducible. And finally, I'd like to mention also that we don't work on 2D slices. We don't work just on 2D images. So the same way that the 2D image can be regarded as a 3D terrain, any 3D image can be regarded as a 4D terrain. So we actually have implemented our algorithm regardless of dimensionality. So our runtimes are explained there for a 128 megavoxel data set. If you'd like more details, go and download the algorithm, play with it, talk to us, etc. Thank you very much.